Hey, what's going on? And we're going to do our first example of the unit, example 4.1. And in this one, we have a kid spinning around on a merry-go-round. So let's get started. We have this merry-go-round. First thing you always want to do, get the right color here, sketch out your problem if you don't have a picture. It helps kind of understand what's going on. So, and of course, drawings will be very terrible, but, we're working with it. So we got this merry-go-round, it's spinning around, and somewhere we have this kid just kind of standing near the edge, and we want to figure out what is the friction force necessary for this person to not fall off the platform. So obviously this is a forces problem. And it's going to be a centripetal forces problem since we have circular motion. And so first thing we want to do is draw a force diagram for the person. So if we just kind of move the person down here, if we looked at the forces that were acting on them, right, we have actually I guess I can just draw it on the merry-go-round. We have the force of gravity that we'll call weight, pulling the person down towards the center of the earth. We have the normal force from the merry-go-round holding up the person. And down here on the person's feet, we have the force of friction. So there's actually a friction force. There should be a horizontal line, but we have a friction force that's pointing towards the center of the circular motion. Because Newton's first law, we know that if all of a sudden this friction force disappeared, it's gone, then this person would just go going in a straight line off of the merry-go-round, and we don't want that to happen. So they're in contact with the ground. They are not sliding, so we know there is a friction force holding them there. Okay. Now in the y direction, up and down, there's only those two forces, so we know those must be equal in magnitude, so we can put little tick marks on there, maybe write it on the side. Okay, and so the only force responsible for the acceleration in this problem, the net force, is coming from that friction force. So we know that when we set up Newton's second law, we'll do it over here on the side, Newton's second law, the net force in the centripetal direction is equal to mass times the acceleration in the centripetal direction, towards the center of the circle. So we need to know what is this centripetal acceleration. So we can go do a little scratch work on the side. Centripetal acceleration is equal to v squared, that's the linear speed right there, it's a v, over the radius of the circular motion. So the problem tells us that this kid is spinning around at 4.5 meters per second, and that value gets squared, and then they are rotating around a radius of 5.8 meters. And when we just punch that into a calculator, we can round a little bit and get that. This comes out to about 3.49 meters per second. That's their centripetal acceleration. So now we're going to come back up to our force equation, right? Because we're trying to solve for what the friction force is. Well, the only force causing this net force in the centripetal direction is friction. And when you look at your force diagram, we only have that one force. So the force of friction is equal to mass times the centripetal acceleration. And we know what the mass is. We know what the centripetal acceleration is, so now it just comes to plugging in some values. So the friction force is equal to their mass, which is 5 kilograms, times the centripetal acceleration. And when you multiply all that out, friction force comes to 17.45 newtons because it is a force. All right, so nothing crazy different. It's still just applying Newton's law. The only difference is when things are spinning around in a circle, the direction of the acceleration is towards the center of that circle. All right, we'll expand on this a little bit more in the coming examples. I will see you guys later.